let's learn how to draw covalent compounds. This is pages 132 and 133 in your notebook. And our goal is to be able to take a compound formula, a covalent compound formula, and then show where the electrons are shared between those atoms. We have to see where electrons are shared in bonds and then where electrons are owned by individual atoms. In order to be successful, we need our periodic table. And it also would probably be helpful if you knew the valence electron numbers for each family group. We've talked about this before, but just as a reminder, everyone in family 1 has 1 valence electron. Everyone in family 2, including the entire middle of the periodic table, has 2 valence electrons. Then we have 3, 4, 5, 6, 7, and 8, with the exception of helium, which only has 2. Okay, and so labeling that is going to be critical to being able to do the math to determine how many electrons we have in the first place. Okay, so the procedure for drawing covalent compounds involves a lot of steps, but the more times you do it, the more you kind of just do the steps naturally. I'm going to teach them each as individual steps, and then we'll learn more as we go on. We go ahead and zoom in here so we can look at the steps first, and then we'll go from there. Okay, so the first thing that we have to be able to do is look up the number of valence electrons for each element involved, and then if that atom has a subscript, you've got to multiply it. Once we know the number of valence electrons for each element, then we add those all up. So for example, if I have CF4, I start with C. I find C on the periodic table, and I see that C has 4 valence electrons. So I write 4 plus. And then I find F. F is here on the periodic table. It has 7 valence electrons. So I say 7, but there are 4 Fs. So I have to multiply that 7 by its subscript. And so 4 plus 7 times 4 gives me a total of 32 valence electrons. And that's how many valence electrons I would have to arrange when I draw the molecule CF4. Okay, so valence electrons multiplied by the subscript, add them up. Now that you have your math, then we actually start to draw it. We're going to start by choosing the least electronegative atom to go in the middle of our drawing. It's going to be our center atom. And so remember, F is the most electronegative. So the farther to the left you get, the less and less electronegative you become. There are some exceptions to this. Family 7 can never go in the middle of the periodic table, as can H. H can never go in the middle of the periodic table. I'm sorry, the middle of a compound. Okay, so least electronegative atom is going to go in the middle. So in this situation, C is the farthest to the left on the periodic table, so it would go in the middle. Then we're going to take the remaining atoms and put them around the central atom. So we would take and place 4 Fs around the central atom. We're going to connect those outside atoms to the central atom with what we call a sigma bond line. A sigma bond line is just a line with 2 electrons on either side, and that represents the 2 shared paired electrons between those 2 atoms. We have to account for those electrons in our total electron count. So for every bond line, we're going to subtract 2 electrons from that credit. Then, once we've subtracted all of our bonds, we're going to go to our outside atoms, and we're going to keep adding electrons that are left over as pairs. Those are dot pairs, so they're always going to show up like this together, and that represents a pair of electrons, until we've satisfied the atom's octet rule. If I hear octet, I think 8. So every atom on the periodic table wants to have 8 valence electrons. That's because the noble gases have 8 valence electrons. And so that's who we want to be. So atoms are trying to share electrons to get that magic number of 8 valence electrons. There are a couple of exceptions to this. H, He, Li, and Be are satisfied with 2 electrons. Generally, you're only going to ever see H and Li when we're doing these. And then B and Al are satisfied with 6 valence electrons. So because that's such an important rule and it's missed pretty frequently, I'm going to make sure that I write pretty large print, B or Al, satisfied with 6. I really need that to stand out to me because that's a commonly missed part of this. But everybody else is going to want to have 8 valence electrons around it. Okay, so we're going to keep adding these electrons as pairs, even to the atom in the center of our picture, until we get this credit number down to 0. We have to get it down to 0. Okay, if you don't get it down to 0, you didn't do something right. If we have to add dots to that central atom, we call those lone pairs. Lone pairs always go on the top of that central atom. And I'll show you what that looks like when we draw it. And then finally, we need to know about, well, what do we do if we've gotten down to 0 and we still have somebody's octet that's not satisfied? In that case, we can create what we call a pi bond or a double bond. A pi bond or a double bond occurs when you share two sets of electrons between two atoms. This happens by first crossing out a pair of electrons that's just on a single atom and then sharing them between the central atom and that outside atom. That second line is called a pi bond, and you can do it again if you need to and get a triple bond. Okay, so what I'm going to do is I'm going to work out the next couple of problems. We're going to follow this procedure. So if you can, I'm going to have to move the camera, but you can kind of follow the list as I draw these. And then I would go back to try to draw them. All right, so CF4. The first thing I have to do is the math. I've already done the math once, but we'll just do it over here again. CF4, C is in the fourth, oh, you can't see that. C is in the fourth column, so I'm going to say 4, plus F was in the seventh column, times 4, and that gives me a total of 32 electrons. Okay, I look at the two atoms, and I notice that C is the atom that is the farthest to the left, so I'm going to place C in the middle, and there are 4 Fs. So I'm going to place 4 Fs around that carbon. I'm going to connect the outside to the central with a sigma bond line, noting that that's 2 electrons. So I put 2 electrons there, 2 electrons there, 2 here, and 2 here. That uses up 2, 4, 6, 8 of my electrons. So I had 32, but now I only have 24. When I look at this, I cover up in my mind everything except for the atom, all the atoms except for the atom I'm looking at. So I'm going to look at this one first, F. Right now, F is claiming 2 electrons around it, but it needs an octet of 8, so I need to give it 6 more electrons. So I can give it 6 more electrons as dot pairs, and now F can claim 8 electrons around it. So I used up 6 dots there, leaving me with 18. But now I need to do it for the next outside atom, so I cover everything else up and I look at F. This F currently is only claiming 2 electrons, so it also needs 6 dots. That leaves me with 12. Do it again. Cover everything up except for the atom in question. So that's 2 electrons, so it needs 6 more to have a total of 8. So I subtract, I'm down to 6. And then I do it again for my atom at the bottom. Okay, I'm down to 0. I had to get down to 0, so that was pretty important. So now what I'm going to do is I am going to check and make sure that everyone's octet is full. This fluorine gets to claim 8, as does this one, and this one. But now I look at the carbon in the middle. If I were to cover up all of the Fs and look at the carbon in the middle, it also gets to claim 8 electrons around it. So carbon also met its octet, and I'm done. Okay, so let's do our next one, AlCl3. I start with math, AlCl3. So I find Al in the periodic table. Move my periodic table over here. Find Al. Al is in the third column, so that's going to be 3. Cl is in the seventh column, so that's going to be 7. So I say Al is 3 plus 7 times 3, and that gives me a total of 24. Of the two atoms, Al is furthest to the left, so I'm going to put Al in the center, and I'm going to give it 3 Cl's around it. Notice that I don't put anything on the top of the atom unless I have to because there's 4 attachments. But otherwise, I'm going to kind of leave the top of the atom open. All right, so I bond it with sigma lines. That's 2 electrons, 4, 6. So I've used 6. That gives me 18 electrons remaining. We start on the outside. I know that this chlorine is claiming 2, so I need to give it 6 more electrons so that it can now claim 8. That leaves me with 12. Do it again. Now that claims 8. And then a final time. That claims 8. And so now I'm down to 0. So now that I'm down to 0, I check and see if everyone's octet is satisfied. This chlorine's claiming 8. Great. Claiming 8. Claiming 8. Al, however, is only claiming 6. But Al is satisfied with 6, so we're okay. So I'm just going to make a little note on my notes that the reason that we're okay is that Al is okay with 6. That's the only way that we're able to leave this drawing as it is because Al is okay with 6. All right, let's do H2O. So I'm going to do the math for H2O over here, H2O. H is in column 1 times 2, because there's 2 of them, plus O is in column 6. That gives me a total of 8 electrons. So I have to decide between H and O who goes in the center. Well, H is furthest to the left, but one of my rules says that H can never go in the middle. So I'm gonna have to place O in the middle. And then I'm gonna place an H on either side. And I'm gonna go ahead and bond it with a sigma bond. So that's 2 electrons and 2 or more electrons. So that's 4 electrons used. That gives me 4 electrons left over. Well, your brain might say, well, put 2 on each outside atom. But hydrogen is satisfied with 2. That means hydrogen never gets anything other than a bond line. So the remaining electrons are going to have to go as lone pairs, which always go on top of the atom. And so we get a lone pair here and a lone pair here. If I go back and check to see who's satisfied, hydrogen only has 2 that it can claim, but hydrogen only wants 2. So both of the hydrogens are satisfied. And if I count around an oxygen, 2, 4, 6, 8, oxygen has what it needs as well. And I got down to 0. So I make a note on the bottom of my page, and I would encourage you to make a note as well, that hydrogen only ever gets a bond. No dots, okay? No dots on hydrogen. It can only ever get a bond. All right, let's look at CO2. Once we get to CO2, some interesting things are going to start to happen. I'm going to move my camera a little so we can see better. Okay, CO2. So CO2. C is 4, O is 6. We say 6 times 2. And so that gives me a total of 16. Carbon is farthest to the left, surrounded by 2 oxygens, 2, 4. That leaves me with 12 left. So I'm going to give 6 to each oxygen because I always satisfy my outside atoms first. So that subtracts 12. I'm down to 0. Now I check my atom for the octet rule. This has an octet. This has an octet, but carbon only has 4 around it. The problem is I'm already down to 0. I don't have any more dot pairs to give it. So what I have to do is cross out and share. So I can cross out a pair of electrons and share it between 2 atoms. That oxygen still gets to claim 8, but now carbon is getting to claim 6. It still needs 2 more, so in an attempt to make it symmetrical, I'm going to do it on the other side as well. And now I have 2 pi bonds. These are pi bonds that were formed, but the only way I can do it is to cross out and share. Okay. And then lastly, I have N2. Now, N2 is different because there's only 2 atoms. There's nobody really in the middle here. When I go to do the math, it's N, which is 5, times 2, so that gives me 10 electrons that I'm working with. So I stake N, and it's just bonded to another N. Again, nobody in the middle because there's just 2 of them. So I put a bond between them, and that's 2 electrons, so I have 8 electrons left over. I'm going to go ahead and just spread them out, 4 on each side. That's a total of 8 electrons, so now I'm down to 0. But the nitrogen on the left only has 6, so I need to cross out and share. But now it has 8. The nitrogen on the other side only has 6, so I need to cross out and share. And now I have 8 around this nitrogen and 8 around this nitrogen, and I end up with a triple bond. But that triple bond could only occur because they crossed out and shared. Okay. So on page 132, your job is going to be to draw those molecules. You're going to do the math. You're going to determine the central atom. You're going to connect with sigma bonds, which all are worth 2. We're going to then place electron dot pairs around the outside atoms until they've met their octet. And then you're going to verify that everyone met their octet once you're down to 0. Don't forget that exception of B and Al being happy with 6 electrons, and the fact that hydrogen can only ever get a single bond. It can never be in the middle. It can never get any dots. If you do not have a satisfied central atom, you've got to cross out and share and kind of do that from either side until you get the answer that you want. All right, I'm going to do 2 examples on page 132, and I'm going to do example SO2 and PF3. So I'm going to slide that over. We're going to look at SO2 and PF3. Okay, so starting with SO2. Find S on the periodic table. It's in family 6, as is oxygen, but I have to do that times 2, so that's going to give me a total of 18 electrons. S is farther away from F, so I'll put S and then an oxygen on either side. 2, 4, so that's going to subtract 4 electrons, leaving me with 14 electrons. So I'm going to put 6 on each O. 6 on each O. That's 12 electrons. That leaves me 2 electrons left. So the only place I can put those 2 electrons is as a lone pair on the central atom. Now I'm down to 0. Remember, I have to get down to 0. Now that I'm down to 0, I'm going to look at this compound, an octet only 6. So I'm going to have to cross out and share because I have no dot pairs left. It does not matter which side you cross out on. I'm going to cross out on this side and share, but you could have done it on this side instead. It's key, though, that you do not do it on both sides. You only have to do it once to give sulfur its octet. The fact that you have 2 different choices here is a process called resonance. We'll learn more about that in the next lesson or so. But resonance basically means that you could have drawn it this way, or you could have put the double bond on the other side. In reality, it's neither of those options. It's kind of a somewhere in between, the bond being on this side and the double bond being on this side and the double bond being on that side. Okay. Last example I'm going to do today is PF3. So I'm going to find P on the periodic table. It's in family 5 plus 7 times 3. That gives me a total of 26 electrons. P is the farthest, and also F can never go in the middle because it's a halogen. So I'm going to give it 3 attachments, noting that I leave the top open. I bond that to 4, 6, so that uses up 6 electrons. I've got 20 left over. I'm going to go ahead and fill out the octet for each of my outside atoms. That uses up 18 electrons, so I have 2 left over. So that means those 2 left over are going to go on top of phosphorus as a lone pair. Okay, so remember, anything attached to the central atom is called a lone pair. You may want to go back over to your notes and mark that as well. So if we go over to number 3, these are called lone pairs because they're central atom attachments. Lone pair. Okay, all right. Hopefully this helps you draw covalent compounds. You can check with me on page 132 to make sure that you've drawn those all correctly.